Okay, so we have been studying integral properties of functions of a complex variable. So we'll look at some very useful results as we go along. But in order to establish some of these, it will be useful to uh, recall a theorem which goes by the name of Green's theorem, which perhaps we have encountered in a study of vector calculus. So in this lecture, we will discuss the Green's theorem. So the Green's theorem pertains to 2D plane, and so you think of a line integral over a closed contour in the xy plane, and so there is a way to connect it to a double integral over the entire region which is enclosed by this closed contour, right? So it's going to help us with contour integrals, functions of a complex variable. So we will discuss it as we go along. But in this lecture, we will look at functions of two real variables, real functions of two variables. And so you have two real valued functions, f of x comma y and g of x comma y, and their first order partial derivatives are continuous throughout some closed region consisting of, there is a simple closed contour, and so we're looking at all these points which are interior to this closed contour, and we think of C in an anti-clockwise sense, right? If you think of it in a clockwise sense, there will be a change of sign. But so let's say that C is described in the anti-clockwise sense. Then so the Green's theorem says that this line integral, which is along a closed path of this function f of x comma y dx plus g of x comma y dy is given by this double integral dou g by dou x minus dou f by dou y, dx dy, where this double integral is taken over the entire area which is enclosed by C. So one can think of this as sort of a 2D version of the Stokes theorem, right? So there is a little more. The Stokes theorem is a bit more general, but let's argue for the Green's theorem, right, in this lecture. And so this is a result which will be useful for us when we study contour integrals involving functions of a complex variable. After all, functions of a complex variable are some special functions of of this kind of two variables x and y, except that we have seen that there are some constraints which come about when you think of a function of a complex variable. Now, one way to argue for this is sort of to consider suppose you have some surface in the 2D plane, and so you break it up into lots of tiny regions, and then you have you can draw lots of small squares, right? Each square has, or a rectangle has, dimensions of dx along the x direction and dy along the y direction. So let's say if you do this, and you can look at how this function f of x comma y varies in some small placket like this, right? So then what you can do is you can imagine taking a contour integral along a path like this, a small tiny path like this. So I should probably highlight it in a different color. And so there's a way to argue that this contour integral, you can show it to be the equivalent of this result that we have here, but inside some small line integral, and then you stitch it along with this line integral. So when you add this line integral plus this line integral, you'll see that you traverse in one of these plackets along the positive sense, but along the negative sense in the other direction. So the contribution from this part will just go away, and likewise you can add this part, and once again this guy is traversed in both directions, and that is true in the other direction as well. So whatever is traversed along this direction will be cancelled by another component from the other direction. So you'll see that eventually all that counts is if you do this kind of an exercise carefully, and if you argue that basically this contour integral will be the sum of all these small pieces of information that you have added from each of these small dx by dy rectangles, right? So you can go about and argue it in this sort of geometrical way. First of all, look at how f of x comma y varies in a small region as x becomes x plus dx and y goes to y plus dy. How does f vary? You can bring in some Taylor expansion argument, right? So I will not go in detail into this line of argument. It is something that you can look up in some textbooks, or you can try to work it out yourself, right? But let's look at another way of seeing this. Let's argue for this in the following way. Suppose you have this contour given by, I have represented it pictorially like here, and I'm thinking of going from point 1 to point 2 in this manner, right? So I have, this contour is made up of two parts. So this is what I'm calling YL of x, which is the lower part, which is a function of x, and as x goes from a to b, and then you go from 2 to 1 along the upper path. So that's what I have labeled as yu. So I can actually think of this entire thing as made up of strips along the vertical direction. So YL to yu, and for which will depend on x. So if I consider this double integral of some function dou f by dou y dx dy, then I can write this as integral a to b dx, right? I consider some small strip dx, and then I x itself will go all the way from a to b. So I have dx a to b and integral dy, y goes from yl to yu. Of course, implicitly yl and yu are both functions of x. And then I have dou f by dou y. So then immediately I can integrate the second one out. So I have integral a to b dx f of x comma yu minus f of x comma yl, right? So x comma yu is from a to b. I can also rewrite this as minus a to b dx. So I bring in the second term first, and there is a minus sign, so minus a to b dx f of x comma yl, and then instead of just writing it as from a to b, I write it from b to a, and for the upper curve, right? So the reason I do that is because it makes sense to go from b to a when I'm considering the upper curve. So f of x comma yu, right? So if you go from b to a, that means you're traversing along this direction. So the minus sign is something that we can deal with, but basically, geometrically, we can see that really this whole thing, if you pull out the minus sign outside, is basically, this line integral from a to b along the lower path plus the line integral from b to a along the upper path, which is nothing but the closed contour integral, right? It's a closed line integral of this function f of x comma y, right? So there is an overall minus sign as well. So what we have seen is, so in other words, integral a to b dx f of x comma yl is really a line integral of f of x comma y along the lower part of C from 1 to 2, and integral b to a dx f of x comma yu is line integral of f of x comma y along the upper part of C from point 2 to 1. So if I use these two results, immediately I see that this closed contour integral f of x comma y dx is actually nothing but minus the double integral dou f by dou y dx dy, right? And we could have done a similar kind of thing, but along the, considering strips along the other direction, right? So instead of vertical strips, if I consider horizontal strips like here, and then I consider a different function. So now, I still have anti-clockwise sense. So I go along from 3 to 4 along the right direction. I call this xr, and then 4 to 3. Now this is x left, xl. And so now if I consider this double integral of a function dou g by dou x dx dy within this entire region which is enclosed by C, then I have integral from C to D dy integral xl to xr dx dou g by dou x, right? And then integral over dx dou g by dou x is something which we can evaluate immediately. So we have integral C to D dy g of xr comma y minus g of xl comma y, which is immediately seen to be a this closed line integral, right? So g of xr comma y is this guy. You go from 3 to 4, and then you have a minus g of xl comma y going from C to D, which is the same as plus g of xl comma y going from 4 to 3, right? So that is the same as this closed line integral. So immediately, if I combine both of these results, we can go ahead and write this closed line integral of f of x comma y dx plus g of x comma y dy along this closed contour in the anti-clockwise sense is the same as dou g by dou x minus dou f by dou y dx dy, which is really nothing but the Green's theorem, right? So this is something that you could have also worked out by the sort of geometrical argument that I gave you, right? So think of a function and how it varies as you change f of x comma y to f of x plus delta x comma y in the vicinity of the point x comma y. You change x to x plus delta x and y to y plus delta x, and then you observe how it changes, and then you try to perform this. Well, what is a double integral here will be just a small area. Consider the area of that small placket that I showed you, and then there's a way to show that that'll be the same as the line integral, and then you stitch together all of this in this geometrical fashion, and then that's going to be the line integral. So that's another alternate way of seeing this, right? So this is the Green's theorem, and yeah, it's important to emphasize that in this in the line integral is taken in the clockwise sense, and the double integral here is carried out over the area enclosed by the closed contour C. Let's look at an example of how this plays out. So suppose you consider the function f of x comma y equal to y squared, and g of x comma y is equal to x. And so if you consider some piecewise regular simple closed curve contour, which is shown like here. Suppose you consider this to be your contour. So you start from the origin, go to the point A, go to the point B, and come back to the point O, right? So this is a piecewise simple closed curve, right? So if you consider some contour like this, you can try out some other and verify it as well. So now we will see that it's actually quite straightforward to verify this. So on OA, dy is equal to 0. Y is not changing, it's only x that changes. And on AB, dx is 0. X is constant and it is equal to 1. And it's only y that is changing. So hence we have, if you look at OA, integral f of x comma y dx plus g of x comma dy is nothing but actually, since dy is 0, it's just f of x comma y dx. But f of x comma y is y squared. So y squared dx. But y itself is 0. So it's actually nothing but 0 for OA. So the OA part gives you nothing but 0 for this set of functions. Now, but if you look at A to B, f of x comma y dx plus g of x comma y dy. Now we have already said that dx is 0 on the line AB, but dy of course is not 0, and then you have to put in x, but x is a constant. So we have, in place of g of x comma y, we have plugged in x, but x is a constant on this line, and x is equal to 1 in fact. So you get integral 0 to 1 dy, which is nothing but 1, right? So there is only this path B to O where we have to evaluate it. So on this curve we see that y is equal to x because it's from 1 to 1 to the origin, 1 comma 1 to the origin, and so it's just the straight line which is at an angle of 45 degrees to the x-axis. So thus we have integral over BO of f of x comma y dx plus g of x comma y dy is nothing but, now we have to do both the functions will play out, y squared dx plus x dy, but y squared is nothing but x squared because y is equal to x along this path. X goes from 1 to 0 and x is just x. In place of dy we put in dx, so both of these terms can be added, so we have x squared plus x times dx, which is just x cubed by 3 plus x squared by 2 from 1 to 0, which is, so at 0 there's nothing, and so it's basically minus 1/3 minus 1/2, which is minus 5/6. So that's the overall line integral over this closed path to 0 or OAB is 1 minus 5/6, which is 1/6. So we have to add the contributions from each of these three pieces, and so we get 1/6 for the line integral. So on the other hand, let's work out the double integral. So the double integral is straightforward. So dou g by dou x is nothing but, so g of x comma y is x, so dou g by dou x is just 1, and on the other hand, dou f by dou y, so f is y squared, dou f by dou y is 2y, so dou f by dou y is 2y, so 1 minus 2y, and then we have to so dy times 1 minus 2y, and then you also have this integral dx, which goes from y to 1, right? So you can fix the limits of integration and immediately work out. So dou g by dou x is 1 and dou f by dou y is y, 2y, and then to ensure that you are in this region, you fix, so dx can go from y to 1, so dx can go from from y to 1, from here to 1, x will go from x equal to y to x equal to 1, and then y will go from 0 to 1, right? So this is one way of identifying the strip. You could have also done it in the other direction. You can convince yourself that you will get the same answer, right? So if you do it carefully, so this integral, this double integral is nothing but 1 minus 2y into 1 minus y. So dx will become x, which is 1 minus y, and then you expand, so you get 1 minus 3y plus 2y squared, which is y minus 3 by 2 y squared plus 2 by 3y cubed from 0 to 1, which is just 1/6. So immediately we see that indeed this double integral is equal to the closed line integral specified according to the Green's theorem, and indeed both of these are equal to 1/6. So indeed we have managed to verify that the Green's theorem holds for this particular case. Okay, so that's all for this lecture. Thank you.